Welcome to This Explainer. I am absolutely thrilled you're joining us today because we're going to tackle one of the most profound, truly mind-bending questions in all of science. What is the actual shape of the universe? Today, we're exploring the fascinating difference between the local geometry of the space we can actually see and the massive, highly theoretical cosmic topology of the entire universe as a whole. So you might want to leave your everyday earthly intuition at the door for this one. Okay, let's dive into this. Does the universe have an edge? Or is it a giant cosmic donut? I know. It sounds like a joke, right? But in physical cosmology, this is a highly serious debate. When you and I look up at the night sky, it just feels like space goes on forever in a straight line. But as you'll see, the actual fabric of the cosmos is far more complex and honestly, potentially a lot stranger than anything we experience here on Earth. To get to the bottom of this, here is our roadmap. We'll start with the observable universe, look at the geometry of space, and see how scientists go about measuring cosmic curvature. Then we'll explore the shape of everything, and finally try to answer, is it infinite or finite? All right, Section 1, the observable universe. Before we can really talk about the shape of everything, we've got to establish our boundaries. The observable universe is a roughly spherical region, extending about 46 billion light-years in absolutely every direction from us. Now, you might be wondering, why is there a limit? Well, looking deep into space is literally exactly the same as looking back in time. In theory, sure, we could look all the way back to the Big Bang, but in practice, we can only see back to the cosmic microwave background, which was formed roughly 370,000 years after the Big Bang. Anything before that time is just entirely opaque to us. So we're basically sitting right in the center of this 46 billion light-year bubble of visibility. So the crucial point is the distinction between local geometry and global topology. Local geometry is just the curvature of the universe that we can actually observe inside our little bubble. Global topology, on the other hand, is the overall shape and structure of the entire universe, including the vast unknown beyond our horizon. If our observable bubble is smaller than the entire universe, which, most scientists totally accept that it is, we just cannot deduce the global topology simply by looking through our telescopes. It's like trying to figure out the shape of the Earth when you can only see your own backyard. Section 2. The geometry of space. Let's step out of our familiar bubble for a second and look at the actual physics of how space behaves. There are essentially three possible types of spatial curvature. According to Einstein's general relativity, mass and energy literally bend the fabric of space itself. This curvature is determined by something called the density parameter, which we represent with the Greek letter omega. If omega equals exactly 1, space is flat, and the angles of a triangle add up to exactly 180 degrees. If omega is greater than 1, we've got a positive curvature, and a triangle's angles add up to more than 180 degrees. And finally, if omega is less than 1, we get a negative curvature, where those angles add up to less than 180. Now, if that non-Euclidean math feels a little too abstract, let's ground it with some relatable analogies. Flat space is super easy. Just picture drawing a triangle on a totally flat sheet of paper. But for positive curvature, imagine the spherical Earth. If you draw a triangle starting from the equator, going straight up to the North Pole, and then back down, you're going to have at least two 90-degree angles. That means the three angles of your triangle are adding up to way more than 180 degrees. Lastly, negative curvature is a lot like the surface of a saddle or maybe a mountain pass, where those angles would actually pinch inward and sum up to less than 180. Section 3. Measuring cosmic curvature. Okay, so it's one thing to have these beautiful mathematical models, but how do scientists actually measure this out there in the cosmos? Well, scientists use a really clever problem-solution approach. They calculate omega by taking the universe's actual average mass energy density, and by the way, that includes baryonic matter, and dark energy, and they divide it by the critical density. Critical density is essentially the exact precise amount of mass and energy required to make the universe perfectly flat. So to figure out the shape of our local geometry, we just have to see how the actual density compares to that critical baseline number. And this brilliantly illustrates just how incredible modern cosmology is. Using data from the WMAP and Planck space observatories, scientists measured the mass energy density of the universe and came up with a total omega of 1.00. And get this, with a tiny margin of error of about 0.02, which is roughly just 0.4%. This is absolutely massive. It proves that, observationally speaking, our observable universe is spatially flat. Space isn't a globe and it isn't a saddle. Locally, at least, it is just like that flat sheet of paper. Moving right along to Section 4, the shape of everything. But remember, local geometry doesn't tell us the whole story, which is exactly why we now need to talk about global topology, the shape of the universe far beyond our observable horizon. Because we can't see the whole thing, physicists have proposed a few mathematically sound, frankly bizarre shapes for the cosmos beyond our view. It's actually playfully fascinating how the greatest mysteries of reality compare to everyday objects. First up, there's the 3 Taurus, which is a multiply-connected space shaped remarkably like a donut. Then, proposed by Jean-Pierre Luminat and his colleagues back in 2003, we have the Poincare dodecahedral space. This one is positively curved and essentially shaped like a giant cosmic soccer ball. Or, hey, we might even be living in a Picard horn, which is a negatively curved space shaped like a massive funnel. Literally any of these could theoretically be the true global shape of our universe. Finally, Section 5, infinite or finite. Let's move to and see how this builds historically, because this debate is ancient. We know our local bubble is flat, but does the universe as a whole go on forever, or does it eventually stop? Back in 384 BC, Aristotle modeled the universe as concentric, completely finite spheres with Earth in the center. Fast forward to 1576 AD, and Thomas Digges takes Copernicus's heliocentric model and actually proposes an infinite universe. By 1917, Albert Einstein flips it again, using general relativity to demonstrate a finite universe. And then, jumping to 2018, modern satellite data from the Planck mission confirms our observable space is stunningly, perfectly flat. Now, here's where we absolutely need to correct a very common textbook error. Lots of textbooks will just boldly tell you that a flat universe is automatically an infinite universe. But consider this critical caveat. A flat universe that is also simply connected implies an infinite universe. That conditional part, the simply connected part, is so vital. Euclidean space is flat, simply connected, and infinite. But remember the 3 Taurus, that donut shape? A torus can actually be mathematically flat, but it is multiply connected, meaning it can be perfectly flat locally, but still totally finite and compact globally. If the universe is indeed a compact, multiply-connected shape like a torus, we can actually find out for sure through something called topological lensing. This is a super cool effect in a small, closed universe that produces multiple images of the exact same distance source in the sky. Think of it kind of like a cosmic hall of mirrors. If you look far enough in one direction, light from a distant galaxy might actually wrap all the way around the universe and hit your telescope from the complete opposite side. Now, what's really interesting about this is if our universe is a finite, closed shape without any edge, light could just endlessly loop around it. Which means we have to ask a genuinely profound question. Are some of the galaxies we see in the absolute deepest parts of the night sky actually just ancient mirrored reflections of our own Milky Way? We haven't found those matched, repeating patterns in the cosmic microwave background just yet, but the search absolutely continues. Next time you look up at the stars, just remember, you might actually be looking at the back of your own cosmic head. Thank you so much for joining me for this explainer. Keep wondering and always keep looking up.